Okay, right. So before we move on to our section on kernels, I'm briefly going to go through the example we did before lunch, just in case anyone had any confusion. I know a few of you did this very quickly, but I think it's important just to review exercises as we go. So I'm on best place to do this. Yep, right, now I can make this bigger. I'm in the directory with all the example data in for the exercise we did before lunch. And the blank example looks like the following. And we're asked to do a couple of things. So we need to declare and allocate some device memory. We need to copy a host array hx to a device array dx, copy device array dx back to the host output, and remember to clean up after ourselves because we need to release device resources at the end. So, and we also want to use our helper macro here to check errors as we go. For this example, we've got the array length we're going to be using defined for us, and the number of blocks and the number of threads per block set above. So we're not going to worry about that. We're not doing any computations, so we actually need these two. But in future examples, be aware these have also been defined above. We have a size calculated for us, so we don't need to do that. And we've already got our host arrays allocated, also defined and then allocated below, and we're certain they've been corrected correctly. So to make sure we do this right, we need to first not do that at all. Mistakes before even start. We need to have a pointer. It's going to be null to start with. And then we need to do an allocation using hipmalloc. We're going to assert on this, make sure this completes correctly. In the size of space that we're allocating. Okay, so this will allocate some location on the device and make it available to us via this pointer that we have on the host. Once again, this pointer we can allocate remotely, but we need access to it on the host side. We then need to copy some information into this array that's sat on the GPU. So then we're going to again do assert to make sure we check for errors. Then going to do a hip mem copy. The destination is the device, so dx. We're copying from the host hx. We've got the size of these, and then we need to pass in the kind of copy that we want to do. So in this case, it's going to be mem copy host to device. Okay. Right, in this case, so we'll see in a moment, we now have some operations or a kernel at this point to do something useful with this data, but in this case, we're just trying to get a sense from the data movement. So we're now going to move it back to the host. In this case, our destination is h out from our source dx, so it's going device to host now. Same size. Or I have errors and we have fun with the compiler. Make sure I spell things correctly. Okay, that should do it. I'm sure I've made a typo somewhere. And finally, we need to free our resources on the device once we're finished. Again, error checking for this. So it's not very C++-y. It won't do this in some reader structure for you. You do need to make sure it's been done. Okay. Then to compile this, we're going to need to make sure we've got loaded a number of modules. So module load log env AMD, module load Rockham, gives us access to HIPCC. We need to set our compute capability. Yeah, XCCL dash AMD dash GFX 90A. Remember, these are these last two modules are features of the Cray environment, not features of the compiler chain needed for HIP code. For completeness, we're making sure we set our host device correct. So these are Milans. Okay, and this is where usually everything is horribly wrong. I'm not going to type this all out because we'll be here forever. So I'll just explain those. So we're using HIPCC to compile. We're telling it we're compiling HIP code. We're setting a C++ standard. We're telling it an environment variable about how we're targeting Rockham, giving us Rockham path. We're talking about which platform we're targeting, the platform an AMD target. We're giving us offload architecture with the code that we haven't just set it in the environment, but to be explicit, I've set it here as well. And then, is that the right file? Yeah. Okay. And now I have some .a.help file. I have some submit scripts so I can submit to the queue. I'm also going to run this. I'm going to run Rockham SMI before I run .a.help. If we submit that and shortcuts on this account, I can see that I'm running by running sq -- me, and I can see that the file is ready to complete. It's completed. So if we look at the Slurm file, hopefully everything's gone right. And yes, so I've got the maximum number of thread blocks, some details, some device information provided, and I get my results. So the number of elements that are correct is equal to the total number of elements that is in the file. Okay, good. So we passed example 1. There's some extensions to this at the end to get you to look at a couple of other features, but I'm not going to go to those in detail. They're more sort of look at the documentation, see what it has to say about certain things. Any other questions related to that example before we move on to doing something slightly more useful with kernels? Okay. I take silence as meaning everything's okay. Please remember we have the course chat available if you want to put things in there. That's readable. Right. Okay, so we've done the initial example. We moved some data between host and device. We understand how the movement works, and we know how to allocate it in a way that means we still have access to the objects from the host. In the case of actually doing useful things, we now need to start exploring kernels, and this will be the next hour-ish up until about 2 o'clock. We'll take a short break, and then we'll do the final session. In a scientific application, a large fraction of the computational effort is spent in kernels. It's natural that kernels, therefore, should be this first target to move work to the GPU. So simply, this is why kernels are called kernels. There's nothing fancy about them, apart from this is the location where we want to do most of our effort. These are often associated with loops, which we can distribute independent iterations between threads and have them work in parallel. So the idea here is that each kernel should have independent operation from each other kernel execution, and then we can send those kernel executions to different threads or different stream processes within a compute unit or stream multiprocessor. So if we follow a simple C-style loop, if we iterate of a loop is independent, we can safely attempt to run each iteration in parallel. Okay, so this is the key bit where you, the programmer, needs to make decisions about ensuring that each iteration of loops you're going to turn into kernels are truly independent. and the choice in which you slice up your particular problem so that's possible is the bit that you need to provide to the program. So we could write a very simple kernel. So to get this to run in parallel over the GPU, we need to write a kernel body. And there, in that case, we have an example. So this is underscore global, says that this is going to run in scope on the device. We're going to call it from the host to execute code on the device. That's what that's saying. It's void. It has no return type. It just has a result. And we're simply going to fill a result with the value, the thread index multiplied by 2. So that each element in the array result has an independent value multiplied by 2. Yeah, as I said, the global is called execution space qualifier. It indicates to the compiler that this is an entry point for the GPU to start executing. The thread index.x is a special variable that HIP provides to allow us to identify the thread. So this is to identify the physical location of execution. And this is where, as I was saying earlier, there can be some confusion about between what's the how I'm distributing the data and what's physically running, which independent source of execution. Because you start to address data structures with individual thread IDs, as you're doing here in result. Okay, so that's how you would write a very simple kernel. We then need the ability to execute this kernel or launch it onto the GPU. We specify to do this a number of blocks and the number of threads per each of those blocks, and then we pass that to the kernel at launch. So we define the kernel above, and then the launch time, we need to provide these triple angle brackets. And these are kind of the launch or execution configuration. Yeah, that's the right phrase. So we have this dim3 blocks and these dim3 threads per block. This is so you can operate over three-dimensional. You can have this multi-dimensional decomposition of your problem. So this is up to 3 dimensions. The simplest case, you just run over X. That's what we're doing here. Right. Yeah, you must arrange the product of the number of blocks, the number of threads per block, giving the correct total length of the problem at hand. And this is on the programmer to do, and we will come on to examples where you need to protect the threads that may run over this. Right, you must have a complete number of blocks. If there is a number of threads without any work to do, you need to tell them to be inactive. Now, that may seem wasteful, but that's up to you, the programmer, to make sure you chunk your work in suitable sizes and pick the size of your blocks appropriately to minimize that. Well, you may be okay with that if it's just a very small fraction of your GPU that's having to sit idle. So this three-dimensional structure is very simple struct that's holding an unsigned int for both blocks and threads per block. This is provided for you by the HIP runtime, so this will be there for you in the headers. Those are the key elements to setting up this. It's defined in the headers. Okay, and you should just be able to use it. I don't think it's defined in any of the documents. I think it's just there. Okay. So that's one block. If we now move to more than one block, it's a little bit more complicated. We now need to consider how we're going to divide up the problem. And we have this extra helper parameter that's available, block dim. So you see they're all block index.x, that's the X dimension. They're block dimension.x, thread index.x. So you have equivalents for Y and Z as well. So threads per block. So in this example, instead of in the below here, instead of setting threads per block has already been defined, and we're just taking the X element of the struct and setting it to threads, a value of threads per block. This capitalized value isn't naturally just available. This is defined in the particular examples we've given. The same with array length is defined at the top of the example programs. You can then calculate the number of blocks you're going to need by dividing this array by the array length by the threads per block, and then passing this into a number of blocks. Block ID is then can then calculated from that and available for you in the runtime. This allows you to then individual blocks to be passed to different compute units. They're all going to execute the instructions within the kernel, but they can act independently if you've organized your calculations in a correct way. We can choose the number of threads per block: 128, 256, 512, 1024. There's usually an upper limit. I think in some cases it's usually like it's either 1024 to 48. I think it's to 1024 in this case. Again, you can probe the device information either with ROCm SMI or with the HIP device control that you upload. That was the end of the last example. You need to calculate the correct number of blocks to cover the problem space, and then those blocks can be distributed across the compute units. So in the above, we've assumed that array length is exactly divisible by threads per block. This is almost never the case, right? Your physics problem does not neatly fit within the design space of a GPU. So you have some internal variables available to you to help figure your location within the problem out in the internals of the kernel, which are just provided in its scope. You have the grid dimension, the number of blocks in the three directions. The block dimension, the number of threads per block, because you may choose different decompositions in different directions. But there may be limits on the total number per block. The block index, which runs from 0 up to the grid dimension in each direction. And then you have the thread index, which runs from 0 up to the block dimension in each of the 3 directions. So this can get quite complicated and a bit confusing, but the best way to learn how to do this is to do some examples. So we'll come on to the main example at the end of this exercise is to go through and try this out. We also need to think about synchronization. So kernels are asynchronous on the host. They will launch and return immediately. In order to be able to ensure the kernel has actually completed, we need to do some form of synchronization. There'll be more complicated versions of synchronization later at different levels. Okay, and just before I go any further, I'll ask a couple of questions in the discussion. So how to define with a 2-dimensional array. So your array can just be passed in to the kernel, and the example we'll look at is doing a matrix calculation later. We'll go through how to use this with 2-dimension. But I could have a block index I, and I could have which covers over X, and I could have another block index Y. So I could have an int J here, which is over the Y dimension, and I can divide it up in 2D. Okay, so that's what we'll look at. So the results in memory is available to all threads in all blocks. Yes, different chunks of it are going to be made available because this is going to be allocated on the device, so then it's made available as sections are required to the various compute units. Okay. So I was talking about synchronization. We need to make sure that we have completed our kernel executions before we move forward. So we have HIP device synchronize. There are multiple levels of synchronization which you can perform related to whether you want to synchronize streams but the easiest thing is the whole device synchronize, which I'm pretty sure covers the whole device. This makes sure everything has reached a certain barrier point. So you're now safe to copy data back from after the synchronized point back to the host from the device, and then do operations on it, because you guarantee that the kernel is completed. Similarly to MPI programming, if you have experience with that, you need to be careful about synchronization. The same rules apply here. Okay, a little bit more about errors. Errors occurring in kernel execution are also asynchronous, which means this can really cause a lot of confusion if you think that if an error is related to a particular kernel or not. So what you'll sometimes see is the ability to peek at the last error, and then synchronize and then do and return information. This queries the error state without altering it. And it will fail if there's errors in the kernel launch itself, not the body of the kernel, if that makes sense. So this is probing what's happening during the kernel. So if you have problems with the configuration of your kernel in any way, it will also error without giving you a sensible piece of information. Okay. So you also need to synchronize errors to collect the information as well. I've talked for another 25 minutes, and it's time to get you to do some more practicals. So we will keep going with this one for about half an hour or so. And this is kind of going to continue from the previous exercise and build upon that. For those people who are going to be really fast at this, there are a couple of extra extensions. One is to look at some extra bits. I'll come to those in a second. So the aim of this is to write an initial kernel, which is just going to multiply some input by a constant factor. You will have to write, so there's a new template available, or you can build on what you've just worked on. If you can, I would build on what you've worked on. If you struggled with that, then use the canned example to give you a leg up. It's absolutely fine. The main point is you try the example. You need to write a kernel prototype in this. You need to perform the scale operation. You need to make sure the data has been moved correctly. And you need to, in the first instance, write an example which only uses thread index, because you're saying that the array length in this example is set to the size of a single block. Okay, that's my set equivalent. In the main part of the program, you'll need to declare initialized variables of type dimension 3 to be able to give threads and blocks and pass them to the execution configuration of the kernel when the kernel is launched. Then you'll need to copy some data back. Once that's been successful, update the kernel and configure it to use more than one block. We will keep the consideration that still the total number of blocks is a whole number. Increase the array size up to 512 or 1024, whatever you think is correct. But make sure you've calculated this in a way that means that this will give just the launch parameters have the right number of blocks to get going. So through that, start to consider non-whole numbers of blocks and how you might, in the passing the correct information to the kernel to make sure this can be accounted for, and also have the correct kernel so that you avoid errors. And finally, if you're really fast, then try implementing DAXP yourself as well. So we'll take the next half hour or so till 2 o'clock looking at this. Please answer any questions you have in the chat, and me and mine will be here to answer anything you might need. So just to go answer your question a bit more, Matthias, there is HIP set device and get device. So you can set the default device, which is a particular API call goes to. There's some more documentation there if you're interested. So answering Des' question, what size of variable do we have to explicitly copy to the device? There's a few kilobytes of constant memory that I think when you pass a value straight into the kernel core it gets copied to, so you've got very limited space. I think it's also shared. We'll discuss this tomorrow afternoon's lecture in detail, but it's limited, so don't use it more. I want to say that to be safe, no, you can't assume that. So if the kernel completes the copy, it's then okay to. You don't know when the kernel's completed is the answer. So Sebastian's asking, can we always safely assume that the GPU calls are run in order? My kernel call being finished when hip memcopy is run. I don't think you can be safe to assume that. I think in this case, the example you're given, it's very unlikely you're going to hit some from out of order, but ideally you should have a synchronization in between to make sure, because effectively the kernel, because the kernel instantly returns, so you've got no guarantee of execution order. When we come on to streams and graphs especially, you can make this more explicit around dependencies. But I don't think it's safe to assume. Okay, it's almost 2 o'clock. My plan was to take a 10-minute break here till about 2:10, and we'll start again. I'll go through this example. It depends how people are going. If people want more time, we can keep looking at this for a little bit longer. But either way, take a short break now till 2:10. So before I look at some solutions for that example, has everyone had a chance to work through that now? Because I can either work through this example now, or we've got time tomorrow morning to go through a couple, review a bit of today's content. So I'm happy if people are still wanting to work on this to defer that. People may be coming back from getting their coffee. I'll give them another minute to respond to that. So maybe there's people just coming back. If we're done, I can go through an example. If we want more time, I can defer that to tomorrow morning. Okay. That's a good smattering of people who seem to have completed it. In that case, what I'll do is I will go through it tomorrow morning as a reinforcement. So I remind people, the next example will kind of cover some of the similar topics. There's another chance to kind of exercise the same techniques. But if you've done it and you think it's correct, then that's great. Okay, so this will be the final session for today. Sorry for the slightly earlier finishing time. We managed to sneak in on the session extra this morning, so we'll likely finish at about 3 o'clock today, but it gives you an hour back to either keep working on this afternoon or get on with some actual work. And we will reconvene tomorrow morning. The final bit we will discuss is a little bit around performance. So we're now on to section 2.3. So we now have a very simple GPU program which can move data from the host to the device can execute a kernel, and it does some form of task. It's not a very useful task, but it does a task. Now I want you to think about what factors can influence the performance of a simple program, and try to understand what controls we have over this. So what we're going to look at is I'm going to describe some principles. Then there's going to be an example, which is going to look at getting some performance out of multi-dimensional examples. So you'll practice using two-dimensional blocking to decompose the problem, and then you will make some choices about how you do the decomposition, and then have a use of ARCHER2 to profile your kernel execution and see how different choices give you different results. So my kind of challenge will be to you to look in the exercises to collect a number of different performance results from ARCHER2, see how your choices do, and see whether you get good performance or not. And then we can compare. And I'll go through that example tomorrow morning at the beginning to kind of refresh, so that those who don't get a chance to get all the way through the profiling bit in the session today have a chance to spend a bit more time this afternoon to do it. Okay, so parallelism. Amdahl's law states that parallel performance of a program is limited by the fraction of code that is serial. So in the GPU context, this has two manifestations. The kernel code is potentially parallel if you write good kernel code. It can still serialize and go horribly wrong. The host code is definitely serial, including sort of host-to-device transfers and things like this. This means additional work is required to expose parallelism or eliminate host operations in favor of device operations. So this is when you see a lot of people try to program these devices who are trying to get as much computation on the device to try and eliminate some of this data movement or these host calls to do data movement. Okay, but the key thing we're going to focus on is occupancy. Potentially the GPU has lots of compute units and stream processors that can be used. Having as many blocks of work available at one time is said to favor high occupancy. This may be thought of simply as having very high degree of thread parallelism, effectively. However, the degree is much higher than you'd expect on a threaded CPU because you have thousands of cores available to you at any one time. So to keep that fed well, your typical GPU kernel wants at least 10,000 or so, thousands and thousands of our threads to be active, or this is units of work available to be done by threads at any one time. This is in order to make sure that you feed the GPU with enough work to do, and to make sure that it can keep doing lots of good parallel effort. So the problem space that we're trying to solve should have a high number of elements. So one criticism or limitation you might see with GPUs is that if you don't have that natural degree of data parallelism in your problem, there may be very little benefit from using a GPU. And this is a perfectly valid criticism of GPUs. If you have things with lots of branching or other models which don't lend themselves to this high degree of data parallelism, then you may not get good performance. And that can take a lot of effort to port programs or models to GPUs, because you really need to think again about how you've split your example, so split your particular case up. And then you're more talking about your parallel design decisions more than you're about the porting problem itself to begin with. Okay, so two-dimensional example is how we're going to sort of try and expose some of this high occupancy and try and demonstrate the benefits of having high occupancy. That's kind of the name of the game for this example. So consider just a simple two-dimensional loop. I've got 512 elements in each direction. If we parallelize the inner loop, we would have work for almost 512 threads. This would be 2 blocks if we were using our block size of 256 threads per block. Okay. So that would be, spread 512 work elements across the available threads. This would be poor occupancy. I would do this incredibly quickly. I can allocate a block per compute unit. I've got 104 compute units available to me on a GPU. I'm really not using all the compute units and a very low occupancy. However, if we parallelize both loops, this would be much better. I now have 512 squared work elements to do, so 262,000 of them. I can divide these up into 1,000 blocks. That's far better. I've now got each block has now got, sorry, each compute unit has potentially got on the order of 10 blocks of work to do. They're going to do the same operations, which is the kernel at the center, the work for each element to do. And that means that the GPU can sustain quite good high performance and switch in bits of work as and when required to hide latency if it needs to go get data and such. And we have to employ a large fraction of the compute units available on our hardware. So this is much better. So this is the type of opportunity we want to parallelize and use on the GPU. So a little bit about how we need to access data to take advantage of this, because it's not always straightforward. I think someone earlier asked about matrices. And this is the bit I always find tricky. I have to review every time I get this course. So given a thread in a CPU favors consecutive memory accesses, so each thread wants a contiguous block of memory. So each streaming process wants a contiguous block of work, work elements to work on in a CPU. And recall that in C that the rightmost index runs fastest in memory. This displays favorable caching behavior if a single thread makes contiguous memory accesses, so that the rightmost is the inner loop. Effectively, I'm going to get some data, I'm going to access each of them contiguously, I'm going to work on them, and then I'm going to change, make a movement when I hit the end of a caching region, ideally. Okay, and then I can organize this in a way that means the size of the blocks I operate on is effective and things like this. I can take advantage of cache hierarchies in the CPU case. For GPUs, you don't want this behavior, you want coalescing behavior. Okay, and that means for GPU global memory, the opposite is effectively true. For the CPU case, the hardware wants to have waveforms, so this is warps or groups of threads, consecutively load memory. So consecutive threads, consecutive processor elements, stream processors access consecutive pieces of memory in a contiguous block. So a whole warp gets a contiguous block, parcels out a bit of it to each processor, and then they do work. So in a one-dimensional example, there's no issue with this because consecutive threads. So effectively here we've removed our loop, single loop here, and we replaced this with block ID like we did above with the results example. We gave it in that case a single value, or we duplicate a value. In this case, we're just putting them equivalent, but it's getting consecutive access to memory locations. Fine, no problem. In 2 dimensions, this gets more complicated. First, consider the example at the top, where now contiguous access on the loop, so the far rightest memory access, each individual thread is going to get access to an individual contiguous block of memory, and that is not favored for access patterns by the GPU. Instead, you want coalesced access, which means that it's actually the J index, which is running over the far right index, is running over each thread getting separate bits of memory. And this is the really important distinction. This is entirely around GPU performance, entirely around getting high occupancy and then accessing your memory in a way that contiguous threads get to contiguous memory, so that you access and operate as a group of threads. Okay. Yeah, so in effect, a given thread is making strided memory access. Is what's favored. Okay. So to try and test this out a bit, and give yourself chance to explore this, we're going to follow this next exercise. We'll examine the issues of parallelism and occupancy. So there's a template example in there again, which follows a similar form as you've had before. You're asked to implement a kernel which computes the following matrix operation. So a matrix element equals a matrix element, which is formed from a constant and two vectors with rows m and columns n, and we want to adopt flattened one-dimensional indexing for this with rows I and columns j. And we're going to try and collect performance information about as we do this. And we're going to collect the performance information using RockProf. The submission script has already got it included, so you don't need to edit that to include it. It will output the results you need in a file called results. I think it's results stats.csv. And when you run, it will produce a bunch of other JSON files, and there may be more information there that you find interesting, but that's the place you really want to be looking. So you check that the vectors have been established, the data's been moved correctly. You're going to check that the memory has been set correctly on the device, because you're going to accumulate on the device, so that better be correct to start with. And then you're going to start with the simplest case where you entirely serialize on the GPU, okay? Only the 0 thread is going to do anything, and then you're going to try and break this out into multiple loops, and these multiple loops out into blocks across multiple dimensions, and see how the performance changes based on your design choices. Okay, that example should keep us going till 3 o'clock at least. I'm happy to hang around a little bit after that if we have questions. And my plan is to go through the example of this tomorrow morning, because it would be really good if people could try to extract data from multiple examples, the choices they made, and plot it and see what they get. You can also vary the size of the array and also deal with the fact if you have if you have array sizes which are not equal to the size of, not divisible by block sizes, if that makes sense, number of threads in a block, and see how you get on. If you've managed to get that to run and get it to work with different array sizes, do try to profile across varying array sizes and see where your limitations are. It's a good example to test where your limits of threads per block and things like this exist. So you get a feeling about the size of problem you can allocate to a given block. Just a little bit extra if you think you managed to get through the exercise quickly. Okay, how are people getting on with the exercise? Are people going through that? Are there any major issues? Yeah, the 2D case is a little bit more tricky. If there's specific examples or bits of code people want to look, either message in the chat to everyone or message me directly. Yeah, so as Ran said in the chat, it's coming up to 3 o'clock now. We'll both be online to answer any questions until 4 p.m. I'm going to take a 5-minute break after this session though, so I won't be around for then. And we're happy to answer further questions, but if people have completed the exercises and want to get on with other things or want to look at this later, don't feel like you have to hang around. We'll be starting again at 10 a.m. tomorrow morning. We'll start with a review of both of the exercise results from this afternoon, followed by looking at managed memory in the morning. During the afternoon, Juan will take over and we will start looking at constant and shared memory before moving on to streams. Please ask any additional questions and we'll try and help you in the next hour. But please feel free to do as you please.